I will now teach you how to find the gradient, the divergence, and the curl in different coordinate systems, taking the spherical polar coordinates as my example. So in the previous video, we looked at the Lamé coefficients. So let me write them here. The Lamé coefficients describe how the coordinates arc elements transform. So for the spherical polar coordinate system, the first Lamé coefficient is just 1, the second is r, and the third is r sine theta. So these Lamé coefficients will tell us how to write the new arc length. The new arc length is 1 times dr r hat plus r times d theta theta hat plus r sine theta times d phi times phi hat. And that's the purpose of the Lamé coefficients, is to give you the general sense of how the arc elements transform. What we're going to do in this video is we're going to use the formulas that I write here, and that's proved in Boas's book, to find the divergence, the gradient, and the curl. The divergence of a scalar, divergence of a vector field, the curl of a vector field, and a gradient of a scalar field psi. So let's proceed to do that. Now when you look at the formula like this, EI hat should be thought of as either r hat, theta hat, or phi hat for this coordinate system that we have. And HI's are the Lamé coefficients I've written there. The del i's refer to the particular values of r, theta, and phi that pair up with di. For example, del 1 refers to del r, del 2 refers to del theta, and del 3 refers to del phi. So those are things that we need to keep in our back of our minds. Let me also write what E1, E2, and E3 are. E1 is r hat, E2 is theta hat, and E3 is phi hat. So with that glossary or dictionary in the corner, which I always encourage you to create before you embark on any of these coordinate transformation type exercises, we can write our answer for what the gradient operator is in spherical polar coordinates. It's going to be r hat times 1 over 1 del r psi plus theta hat 1 over r, because that's h2, del theta psi plus phi hat 1 over r sine theta del phi psi. Now you observe this famous coordinate singularity at theta equals pi and theta equals 0. It's called the polar singularity. The third component of the gradient simply blows up at theta equals 0. So that's something that you'll deal with in certain coordinate systems. So in full glory, then, this would be del r psi r hat plus 1 over r del theta psi theta hat plus 1 over r sine theta del phi psi phi hat. And that's how you find the gradient. And here we are going to assume that this object psi is a function of the appropriate variables, namely r, theta, and phi. Now the recipe for finding the divergence of something is the following. It's 1 over hi hj hk del I hj hk vi. Let me explain what this means. By the Einstein summation convention, you have a cyclic sum over everything. So this is a cyclic sum, which I'll write like that. Observe how the cyclic sum is evaluated. First, I'll write 1 over h1, h2, h3. So I is 1, which means this is going to be del 1, h2, h3, v1. The second term is going to be 1 over cyclic, right? So it's going to be h2 then. h2, h3, h1. If you like, you can make a 1, 2, 3 clock to guide you. And then you have the same pattern. It's going to be del 2 of h3, h1, v2. And the last term is going to be 1 over 3, 1, 2. Del 3 of h1, h2, v3. Done. Now all you have to do is substitute the relevant things. Fortunately for us, there's always a h1, h2, h3 in the denominator, so that's going to be r squared sine theta. So I'll write that as 1 over r squared sine theta. And then all I have to worry about are these little things here. Del 1 is just del r, h2, h3. That's going to be those two things together. So that's r squared sine theta times a component, or the component of r, the r component of v. So separately realize that v of r theta phi is written now as Vr of r theta phi r hat plus V theta of r theta phi theta hat plus V phi of r theta and phi hat. That's a full blown meaning of what a vector field is. The r theta and phi components are themselves functions of r theta and phi. The vector field is a very fearsome object. So this gives me the second component is just del theta of h2 h1 h3 h1 versus r sine theta v theta, and then lastly del phi of h1 h2, that's just r times v phi. Done. We have found the divergence of a vector field. That same vector field, let's now find its curl. The curl is quite a beast to find. The formula for the curl is, once again, it's a cyclic sum of epsilon ijk e sub I hat divided by the remaining lames. So when you pick a I, you only put the remaining lames down there, and then del j of just the third lame here, vk. And that's also a cyclic sum. Let's try to figure that out. Let me choose the smallest font I can get. So using again the 1, 2, 3 clock, I'm going to get 1, 2, 3 E1 hat over, it's always best to write everything in terms of the lame first and then substitute your specific things. So del 3 H3 V3, that's not bad at all. Plus, now all I have to do is permute these indices. So that's going to be 1, 3, 2. Wait a sec. I have to do all possible permutations of 2 and 3 with 1 over there. So I have to write this as 1, 3, 2. So there are going to be 6 terms. E1 over H3 H2, which really doesn't matter in this case, but 1, 3, 2 and 1, 2, 3 are opposite of each other, so there'll be a negative sign, relative negative sign there. Del 3 of H2 V2. Observe also that when I interchange the 2 and the 3, what gets eaten up here is the second component multiplied by the second lame. So that's the first term. Then I have two more terms like that. Epsilon 231 E2 31, and then I have the del of the last thing. So that's going to be del the del j. This is the jth position, so that's going to be the 3 here. Del 3 h1 v1. What's inside is the last thing. And here now I have to interchange 1 and 3. So now I get the same E2 above, but here I interchange 1 and 3, which really doesn't matter down here, but it helps us remember that what we have now is the middle term, which is del 1, and that's H3 V3. Last term, epsilon 312 E3. Let me also write the other term, epsilon 312 E3, and here I have H1 H2, and here I have 321 H2 H1, and that's del middle term 1, outer term H2 V2, and then here it's del middle term is 2, outer term is H1 V1. Now all we have to do is put values in, and that's the last and final step in finding the curl of a vector field in arbitrary coordinate systems. So first of all, the first two terms can be combined, because if epsilon 1, 2, 3 is plus 1, epsilon 1, 3, 2 is minus 1. Likewise, that's plus 1, that's minus 1, plus 1, minus 1. So we can easily combine these. E1 hat is just ER. H2, H3 is common to both, and from our glossary, H2, H3 is just R squared sine theta. So I'm going to write this as R squared sine theta, and then go inside and write the derivative terms from there. So del 3 is the first one, gives me actually this was 2, del 2, because I just noticed that this is 2 and that should be 2, 3, 3. Let me just make sure I got this right. Yeah, everything else is good. So del 2 is actually going to be del theta, and H3 is R sine theta from here, V phi, minus del 3, which is phi, H2, which is R, V2, which is V theta. So that's the R hat component of the curl. Next, the theta hat component of the curl. So this is going to be E theta hat over H3 H1. Well, that's going to be R sine theta times 1, which is basically R sine theta. And then that's del phi, because 3 is phi. H1 is 1, so that's just VR. Del 1 is R, and then I have H3, which is R sine theta, V phi. Now just to make you observe, V phi is not just some constant. It's a function itself of R theta and phi. So when you actually differentiate this, you're going to get a whole plethora of terms. So this is not going to be an easy, curl is not going to be an easy thing at all. So this again, E3 hat is E phi divided by H2 H1, which is just R, because H1 is 1 and H2 is R, times, now I have del 1, which is del R, h2, which is r v theta, minus del 2, which is del theta, of h1, which is 1, times vr. We're done. That's a curl in spherical polar coordinates.